Hi everyone, this is Professor Mayunger and you are watching EUDA Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show finite element analysis of an overhanging beam under uniformly distributed load and also one concentrated load. Let us see the statement of the problem. A beam ABCD is loaded as shown in figure. Draw the SFD and BMT and also the point of counterflexure of the beam using ANSYS mechanical APDL and compare the results. So it is given that total length of the beam is actually 4 meter and we are having two defined loads. One uniformly distributed load is spanning from A to B with a load of 2 kN per meter and a point load of 4 kN is applied at location C. We need to find out the shear force and bending moment diagram of this beam under this specific load, and also we need to find the point of counterflexure, that means where bending moment is changing its sign. That is the location P to be find out, at which point bending moment will be changing its sign, that to be find out. Okay, so without wasting time, let us start our analysis using ANSYS mechanical APDL. Okay, so let us close this one. First of all, we need to create a directory, and in that directory we need to save everything. Next to that, we need to change the title of this one, and that will come from file, change title, and we can name this one as FA9. Okay, to see the title, plot replot, it will show the title at the lower left corner, right? It is visible at the lower left corner. Now we need to select what type of analysis it is, and that will come from preferences. It is a structural analysis. Okay, and next to that we need to provide elemental properties, that will come from preprocessor. So element type, add read delete, we need to add it, and we are considering beam with 3D finite strain and element type reference number is 1. And from options we can select element behavior as cubic form. Okay, let us close it. Next to that we need to provide material properties, and we know that our material is having modulus of elasticity of 2 into 10⁻11 Newton per meter square and Poisson's ratio as 0.3. Okay, so material models: structural, linear, elastic and isotropic, and modulus of elasticity is 2E11 and Poisson's ratio is 0.3. Okay, let us close this one. Now sections, beam, common sections. As usual, it will be having breadth of 0.01 meter and height also 0.01 meter. It is a square cross section, right? So breadth equal to 0.01 meter and height also 0.01 meter. Okay, done. Next to that, we need to start modeling, and better to create key points in active coordinate system. Let us see the drawing again for the location of key points. The total span of this beam is 4 meter, and first key point will be created at origin, second one will be at a distance of 1 meter from origin, third one at a distance of 2 meter from origin, and the fourth one at a distance of 4 meter from origin. So it will be 0, 1, 2 and 4, right? So first key point we are creating at origin, apply. Second one will be created at a distance of 1 meter, apply. Third one at a distance of 2 meter, apply. Fourth one at a distance of 4 meter, apply. Now for orientation of the beam, let us select one specific key point at a distance of x equal to 0 and y equal to -2. Okay, all the key points are made. Now we need to join all these key points in the form of a line. So lines, straight lines, you can select key point 1 and 2, then key point 2 and 3, and finally key point 3 and 4. All the lines are joined. Okay, next to that we need to mesh it. So meshing, mesh attributes, and we need to consider the extra key point 5 for this orientation of the beam. So we can select all lines, and we are considering that key point also to be taken into consideration. Okay, so let us select key point 5 for this orientation. Okay, done. Now we need to select size controls for meshing, and we are considering manual size, and lines. Let us select all lines, and we are considering number of elemental division for each line equal to 10. For better meshing, we can have the numbers to be more, but in this case we are considering only 10 divisions. Okay, right? Now finally we can mesh it. So lines, pick all, meshing is done. Now we need to apply our boundary conditions, and that will start from loading. Analysis type, it is a new analysis and it is a static structural analysis. Okay, next to that we need to define loads, apply structural displacement on key points. Let us see the drawing again to see the actual location of different supports and loading. You can see that first support will be at location B at a distance of 1 meter from left hand side, and another support will be there at extreme right hand side. So two supports will be there, right? Okay, for that we need to select the specific lines. So plot lines, one support will be there at this location and another will be at this location, right? So apply on key points. We need to select specific locations. Let us select extreme right hand side node, apply, and it will be restricted to move along X, Y, Z, and also it will be having restricted rotation along X and Y. It will be only allowed to rotate along Z only. Apply. First one is mid. Now second one will be applied at this location. Selected. Okay. And here in this case it will be restricted to move along Y and Z, and also restricted rotation along X and Y. Done. Next to that we need to apply our specific loading. Let us see the question again. One concentrated load of 4 kN will be applied at location C, and uniformly distributed load of 2 kN per meter will be spanning from A to B, right? So force moment on key points. Let us select this location. Okay, and the force is along Y direction, it is Fy, and the loading is 4000 Newton. So as it is in the downward direction, it will be minus 4000 Newton or 4 kilonewton. Okay, it is applied at this location. Now uniform distributed loading will be applied at the extreme left hand side, spanning from this location to that location. So pressure on beams, you can select a box for selecting all the nodes. Selected. Okay, and as it is in the downward direction, it will be minus 2000 at node number 1, and it will be finishing also with the same value, minus 2000. Okay, done. So we applied all our required boundary conditions. Now we can solve it. So solution, solve current LS. If everything is right, it will show solution is done. Okay, so it is showing solution is done, so everything is perfect. We can see our results from general post-processing. Okay, so let us close it. And general post-processing, first of all we need to read our results from last set. Next to that we need to create the elemental table, element table, define table. We need to add it, and we know that for seeing the bending moment and shear force we need to depend on specific numbers. For bending moment we need to depend on SMIS 2 and SMIS 15. Similarly for shear force you need to depend on numbers like SMIS 5 and SMIS 18, right? So from drop down menu we can select by sequence number, and it will be SMIS 2 for bending moment. Apply, and the next one again by sequence number, and SMIS 15 for bending moment. Applied. The third one again by sequence number, and it will be SMIS 5. Apply, and the last one again by sequence number, and it will be SMIS 18. So we selected all the numbers, SMIS 2 and 15 for bending moment and SMIS 5 and 18 for shear force. Okay, let us close it. Now we want to see our results from listing. So list results, and first of all we want to see reaction solution. Let us select all items, and you can see that maximum reaction is occurring at node number 2. It is 5000 Newton, and at node number 42 it is 10,000 Newton, right? You can see the question paper also again. It is 5000 and 10,000 Newton, right? Let us see the question paper. It is also showing the exactly same thing. It is showing at B it is 5000 Newton or 5 kilonewton, and at extreme right hand side it is 1 kilonewton or 1000 Newton, right? Okay. Next to that we'll see our results of bending moment and shear force together with listing results, right? So you can see element table data, and let us select all the numbers SMS 2 and 15 for bending moment, and again SMS 5 and 18 for shear force. We want to see all the results together. Okay, we can see here we're having total 30 numbers of nodes, and in each case you can see shear force and bending moment diagrams. First two columns represented by SMIS 2 and SMIS 15 will represent bending moment diagram, and third and fourth column represented by SMIS 5 and SMIS 18 will represent shear force diagram, and each point or each node is representing shear force and bending moment at specific locations. And you can see here at the left hand side, maximum bending moment is occurring at node number 21. It is 2000 Newton meter or 2 kilonewton meter, and minimum is occurring at node number 11. It is minus 1000 Newton meter or minus 1 kilonewton meter. Similarly, maximum shear force is occurring at node number 11. It is 3000 Newton or 3 kilonewton, and minimum is occurring at node number 10. It is minus 1800 Newton. Let us see this one from the question paper itself. It is showing that maximum bending moment is actually 2 kilonewton occurring at location C, and minimum one is actually 1 kilonewton occurring at B. Shear force also it is showing that maximum shear force is actually 3 kilonewton and minimum is 2 kilonewton. So we can check it here itself. Maximum is occurring at node number 11. It is 3 kilonewton or 3000 Newton, and minimum is occurring at node number 10. It is minus 2000 Newton or minus 2 kilonewton. So it is exactly same what we got in our theoretical results, right? Next to that we want to plot our results, right? So plot results. Can do plot line elemental response, and you want to see bending moments. So it will be SMIS 2 and SMIS 15. Okay, this is representing bending moment diagram, and you can see here maximum bending moment is occurring at this point. It is 2000 Newton meter or 2 kilonewton meter, and minimum is occurring at this location represented by blue color. It is minus 1000 Newton meter or minus 1 kilonewton meter. Okay, you can see this one from our question also. It is showing exactly same. Maximum is 2 kilonewton meter and minimum is 1 kilonewton meter. It is exactly same. Now want to see the point of contact flexure. That means the location where the bending moment changes its sign. It is at location P. So that to be shown from ANSYS mechanical ideal. This is the point of contact flexure. You can see it. To see the point of contact flexure, we can show the node numbers also. So plot controls, numbering, and we can select node numbers on. Okay, reaching all the nodes for a specific location. You can see near node number 25, the bending moment is changing its sign. Let us see in a better way. So plot controls, pan, zoom, rotate, box zoom. You can select this one in the form of a box. You can see near node 25, bending moment is changing its sign, right? So it is very close to 25. We can find the point of contact flexure. To have better results, we can go for better meshing. In that case, the node will be passing through this specific location of point of contact flexure, and we can find better results, right? Okay. Next to that, we're going to see displacement of each node along y direction. So nodal solution, dweb solution, and y component of displacement. Okay, you can see the displacement of each node, and you can see the maximum displacement is occurring at this location down blue line is minus 8.171, right? And that can be viewed in the form of listing also. So we can go for list results and nodal solution, dweb solution, and we want to see y component of displacement, that is showing displacement of defined nodes. And you can see that maximum displacement is occurring at node number 44. It is minus 8.1710, right? At node number 44. We can look at that node also. At node number 44, maximum displacement is occurring. Let us see that location, node number 44. It is at this location. So here at this location, we are having maximum displacement, right? Okay, fine. Next to that, we want to see the animation of this beam. For that, we need to see the solid beam or the beam in 3D format that we checked from here. Plot controls, style, size and shape, and display of elements should be on. Okay, and you can see this is the beam in 3D format. For better understanding, you can see the oblique view. So this is the beam in 3D format with a specific cross section of 0.1 meter by 0.1 meter, right? Now I want to see the animation of this one. So plot controls, animate, deform results, and with the default setup, we want to see the displacement in y direction, uy. Okay, you can see how the beam is vibrating. To see the vibration or deformation in a better way, let us change the delay period. So this way the beam will be vibrating, right? Let us close this one. So this is all about today's video. This was a very simple analysis of an overhanging beam under uniformly distributed load and also one concentrated point load. And in this analysis, we found the shear force and bending moment diagram and also the point of contact flexure, and that was validated or compared with the theoretical results, and we found the exact same solution what we got in our theoretical result. So this is all about today's video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.